Hi, in this video we're going to be talking about the analytical applications of high-performance liquid chromatography, or HPLC. It's important to remember that when we're talking about liquid chromatography, what we are in fact specifying is the fact that the mobile phase traveling through the column is a liquid solvent. And in this particular case, we are going to be talking about reverse phase HPLC, where the liquid mobile phase is going to be a polar solvent and the stationary phase is going to be a nonpolar compound. That way, the equilibrium that is being set up between the two immiscible phases is going to be based on the polarity of the molecules. A molecule that is more polar is going to be eluted off the column first because it will spend more time in the mobile phase. A compound that is more nonpolar will actually stick to the stationary phase more, or be dissolved into the stationary phase, and so therefore will have a longer retention time. Separation of the two compounds in the chromatogram is going to occur because of the polarity of the molecules. In a general block diagram, in order to do the HPLC experiment, you need some reservoir of the mobile phase that you're going to be using, or the HPLC solvent. In this particular case, a polar mobile phase. But that solvent needs to be pushed through the HPLC column. That's done through the use of a high-performance pump. The pump pushes the solvent, the sample is injected into the flow, and then the mixture is pushed by the pump through the HPLC column. It's important to remember at this point that the column itself and the chromatography portion of the experiment is only for the separation of the components of the mixture. You still need a separate detector in order to quantify those components. Typically in an HPLC experiment, that detector is a UV absorption. So as the mixture exits the column, it goes past a UV detector which measures the absorbance as a function of time. Quantification then is done based on the area or the absorbance of those peaks in the chromatogram. Let's talk about a specific example of this. In this experiment, what we're going to want to do is determine the amount of acetaminophen and aspirin in a single tablet of an over-the-counter analgesic. Quantitation is going to be done by separation of the different components with HPLC, and then quantification being done by a UV detector. All right, so in this particular example, a single tablet of an analgesic containing acetaminophen and aspirin is dissolved into 1 liter of solution. That means all of the milligrams of the aspirin and the acetaminophen are now dissolved into 1,000 milliliters. We are going to analyze that unknown using HPLC. I'm going to add at this point that during the course of this experiment, it's going to be important to use an internal standard to make sure that we can compare injections to injections. So, If we took our initial mixture containing the tablet and we injected it onto the HPLC, we would expect to see a separation of the two different components. The acetaminophen, being a little more polar, is going to have a shorter retention time. The aspirin, being just slightly more nonpolar, is going to have a somewhat longer retention time. If we inject those two components onto the HPLC column, we would expect to see the two peaks. The area of those peaks is proportional to the concentration. But you have to remember that the detector that you're using is an absorbance detector. So you still have to concern yourself with the molar absorptivity. That means the slope, or you still have to use standards to know, how big is that absorbance? How does that compare to the concentration? Furthermore, these areas can also be affected by the injection volume or by the experimental setup or the detector that you're using. So it's important that we use what is referred to as an internal standard. If we injected just the mixture containing the acetaminophen and the aspirin, we see these two peaks, and we could get the integrated area of those peaks and assume that that's proportional to their concentrations, but we wouldn't know the absolute concentrations. So just like in a UV-Vis experiment, we still have to do a standard injection so that we get the response factor of the different compounds. In an HPLC experiment, this term response factor is equivalent to talking about the sensitivity or the slope or the response of the detector to the different components. Acetaminophen will have a slightly different response factor than aspirin. In addition, to take into account the different effects of injection volumes or possible experimental changes, we also use an internal standard. So in this particular case, we put benzoic acid in, which has a retention time of just about 7.5 minutes. If we put that internal standard in at the same concentration, that means that this area should remain constant. If it doesn't remain constant, that means that we have had changes to injection volume or other experimental changes. But we have an internal standard to always compare things to. So we took our original mixture and we spiked it with benzoic acid at a concentration of 0.35 milligrams per milliliter. This first chromatogram represents the areas of the peak created by known concentrations. This one chromatogram is going to give us our standards for both the acetaminophen and the aspirin. We can then inject our unknown, and we can see the areas of the acetaminophen and the aspirin relative to the benzoic acid in our unknown. And so we have our standard and we have our unknown. If we're going to calculate the concentration in our unknown, the first thing we need to do is figure out what is the response factor for the acetaminophen and what is the response factor for the aspirin. Again, that's like trying to determine the sensitivity of the UV detector for these two components. Because we want to make it a standard comparison, rather than using just the area of the acetaminophen and the aspirin, what we're going to do is use it as a percent area relative to the area of the internal standard. So in this experiment, what we need to do is take the area of the acetaminophen and divide it by the area of the internal standard to get a relative area in the standard peak. We do that for both the acetaminophen and the aspirin. So here we know what is the relative area of this compared to that. This will be the area that we use. Rather than using the absolute areas, we are going to use the relative areas as a measure of concentration. In the standard, we know the concentration, so we can create, well, the equivalent of a 1-point slope. We can calculate the response factor, which is the concentration divided by the relative area. And that gets us a response factor of 0.103 milligrams per milliliter per percent area. So the units of the response factor is its concentration divided by its percent area. Now, if we look at the unknown, which is our one tablet dissolved in 1,000 milliliters, then spiked to the same concentration of benzoic acid, we can look at the relative area of the acetaminophen and the aspirin in the unknown solution. So now we take the chromatogram from our unknown solution and we again find the relative area of the acetaminophen and the aspirin in the unknown. In the unknown solution, the relative area is 0.92 and the aspirin is still around 0.105. If we take that relative area, so 0.92, times the response factor of 0.103 milligrams per milliliter over percent area, the percent area is going to cancel out, and we're going to find out that that unknown solution is 0.095 milligrams per milliliter. This tells us what the concentration of the unknown solution is. Since we know what the concentration of the unknown solution is, it's a pretty easy feat to calculate what is the milligrams of the tablet, because remember, we took one tablet and we dissolved it into 1,000 milliliters. So all of the acetaminophen in that tablet was dissolved into 1,000 milliliters. So if we had 1,000 milliliters of the solution and we knew the concentration was 0.095 milligrams per milliliter, that means there must have been 95 milligrams of the acetaminophen in the tablet. By that same approach, if we had a concentration of 0.12 milligrams per milliliter of the aspirin, and that 1,000 milliliters is multiplied by 0.12 milligrams per milliliter, that tablet must have had 120 milligrams of aspirin. Therefore, using a standard chromatogram, which gives us the response factors, and a chromatogram of an unknown mixture, we could calculate that the tablet contained 95 milligrams of acetaminophen and 120 milligrams of the aspirin.